Hi, my name is Adrienne Hoarfrost. My proposal is to use self-taught learning to learn high-level features of microbial communities and to apply these features to predict microbial impacts on Earth system processes.
Microbial communities are central to shaping the geochemical environment around us. They produce half the oxygen we breathe, they impact the amount of CO2 in the atmosphere, and the amount of carbon preserved over ecological and geological timescales. But microbial information is virtually absent from Earth system models. This is because these are incredibly complex systems, both in the microbial communities themselves and in the complexity of their interactions with their environment, and this makes them hard to predict from direct trait-based modeling. Plus, gathering samples from these environments can be difficult and expensive, where, for example, you're spending tens of thousands of dollars a day to operate a research vessel to gather your tens or hundreds of samples that you're able to take.
So for these reasons, I think environmental microbial communities are a perfect use case for deep learning. I propose to leverage the rapidly growing pool of next-generation sequencing data to do unsupervised feature learning on microbial communities in general that can then be used to predict biogeochemical outcomes in environmental communities where we have relatively few labeled examples.
Using a sequencing data discovery tool I built, I've identified the 1 million or so whole community metagenomes that are in existence. Pre-processing this data is really important and will require mapping every sample to a common gene reference to get counts of genes of every sample. Current gene references only represent the less than 1% of microbes for which we have representative genomes, so I plan to create a novel, non-redundant gene database from the million metagenomes themselves by doing a massive co-assembly of these samples. This is a truly absurd computational task that can only be done because of recent advances in distributed algorithms for assembly. High-level features of microbial communities will be learned on a deep denoising autoencoder architecture, and finally these features can be transferred to predict rates of biogeochemical processes from microbial information on our labeled samples.
I really think an approach like this is the missing link in understanding and predicting the coevolution of life and Earth. And in the process, it'll produce pre-processing tools and high-level features that will be useful in virtually every bioinformatics prediction task. I'm really excited about this project, and I hope AI Grant is too. Thanks.